So welcome everyone. My name is Hilmi. I'm a master's student under the supervision of Shao and Mario, whose names are also in the paper. Um, so I'll be talking about today the article version of my master's thesis named Investigating the Effects of Spanwise Transversal Traveling Waves on a Turbulent Compressible Flat Plate Flow with the aid of a deep autoencoder network, which has admittedly quite a long name, but I hope you will like the presentation today. And I'd like to begin directly with our motivation in the aviation industry. The skin fraction makes up almost half of the total drag, which makes it a important component that is under question in all applications. And in this context, machine learning is already used for drag reduction and also dimensionality reductions or mode decompositions before. However, the prior research was limited to relatively lower Mach numbers and simpler flows like a flow around the cylinder. The presentation, as well as the work, consists mainly of two parts: the physical aspects, and namely drag reduction and its mechanisms behind it, and the machine learning part, so our autoencoder structure. And to begin, I will try to give you some critical backgrounds and talk about key concepts, then present the results, and then we'll wrap it up with the summary and a brief future outlook. So we can directly move on to theoretical backgrounds. What we are doing is we are using spanwise transversal traveling waves with the main target of relocating quasi-streamwise vortices, which are traditionally located in the near wall, and we're trying to relocate them to the outer wall regions. And on the top right corner from the animation, you can see the reference and the actuated cases, as well as the actuated parameters that we used for a Mach number of 0.7. So in part B of this animation, you can see that we have a spanwise sinusoidal function that is deforming the wall, as well as a shock wave that is traveling along the spanwise direction. And on the bottom left, we have our computational setup where we start with a non-actuated flat plate flow, and then it converts into a fully actuated flow. Then a spatial transition is done, and it ends with a non-actuated flow again. And here, right below this figure, you can see the function that we use to give the wall its wavy motion. And on the bottom right corner, we can immediately see our first result for a Mach number of 0.7, which is the reduction of skin friction coefficient, where we achieved almost 26.5% average drag reduction between the reference and actuated cases. And in order to understand the mechanisms behind this, first we have to take a look at quasi-streamwise vortices. Here in this figure, you can directly recognize it. It's a traditional turbulent boundary layer consisting of the viscous sublayer and the buffer layer, as well as the log region and the wake region. And on the gray plate to the right side of the figure, we have straight lines, which represent the quasi-streamwise vortices that are aligned in the streamwise direction and dominating the flow in the near wall region. However, their effects start to fade away as we move further away from the wall, as they leave their presence to horseshoe vortices. And the QSVs are important in drag reduction because they are the primary generator of Reynolds stress, which is a key characteristic of turbulent flows, and Reynolds stresses in turn generate shear stress, which results in the production of drag. And here on the top figure, we can see our resulting flow field and instantaneous snapshot of it. And what we have is a highly turbulent flow, meaning that there will be large scale as well as small scale structures, wide range of them. And we have a shock wave, as mentioned before, that is traveling along the spanwise direction with the wave. And as the shock wave interacts with the flow, it reduces the number and the sizes of the quasi-streamwise vortices. And on the bottom corner, we have a probability density function plotted over the non-dimensionalized wall normal direction over 20 consecutive time steps for the reference and actuated cases. And what we can recognize immediately is that between the reference and actuated cases, the number of the statistics of QSVs being in the region is considerably lower in the actuated case compared to the reference case, which would expectedly result in a reduction of the Reynolds stresses. Here in this plot, we can see the reference and actuated cases for the symmetric components of the Reynolds stresses. And as we can recognize from the graph between the reference and actuated cases, the Reynolds stresses are, all three components of the Reynolds stresses are decreasing in a considerable way, which another key indicator that this method is working is the reduction of wall vorticity fluctuations, which is also a key indicator of the presence of vortices in the near wall region. Here again, we have the symmetric components for the streamwise, spanwise, and the wall normal directions for the vorticity fluctuations. And what we can see is that between the reference and actuated cases, these vorticity fluctuations are also decreasing. Hence, the drag reduction is achieved. And in order to further analyze it, we developed an deep autoencoder model. What this model does is takes the snapshots in the YZ plane and compresses them to a very low resolution picture by the encoder architecture. And from the latent space where the low resolution image is located, this image is taken by different modes or decoders, as we might say, and these decoders all produce their own output, which are then added at the end in order to get the reconstructed image. Here we are depicting with two decoders, but we use two for 16, 32, and 64 decoder configurations. And the main target here is to produce an output image which is as similar as possible to the input image. And the hyperparameters we used are located on the top boxes. We had a batch size of 32, and as an optimizer, we used Adam. And for loss function, we had mean squared error, which is a common practice. And as for the activation functions, which are actually the parameters that introduce nonlinearity, we use hyperbolic tangent and rectified linear unit or ReLU. And before going to the results, first we had to validate our model. Here we see the training and validation loss plotted over the epochs for one of our simulations. And as you might recognize that both the training and validation losses show a converging behavior in a good fashion. Although there are some small fluctuations along the way, those are within the plausible range. However, after epoch 1000, we see some early signs of overfitting where the training loss is following a steady trend, whereas the validation loss is fluctuating. And that's when our early stopping criteria comes into play, meaning that if the validation loss doesn't improve for 200 consecutive epochs, the model stops completely in order to prevent overfitting. So now that we have validated our model, we can jump into our initial results. Here we have the original images for the velocity components U, V, W, and P on the left side. And as we move on to the right, we have the reconstructed images from 2, 16, 32, and 64 modes with the mean squared error written in the bottom boxes. And what we can see from these initial images is that the reconstructed images look somewhat similar to the original image, where the main large-scale characteristics like the shock wave is captured. However, the detailed flow properties like high-frequency events like the turbulence or small-scale structures are not exactly captured, although the configurations with 32 modes and 64 modes show some initial signs of turbulence. The images do not look exactly similar. So to give a quick conclusion on the simple model, here we have the original image with the 64 modes, reconstructed images. And what we can see is 64 mode is the best model because as we increase the model complexity increases and its ability to reconstruct the image increases. And in the 64 mode configuration, we can see that the main patterns are captured. However, the small scales are not exactly captured, and increasing the modes from 2 modes to 64 modes did not achieve as much as we would like, although there are some minor improvements. That means that further improvements were needed, and what we thought was, why not increase the complexity of the model by multiplying the number of future maps in each convolutional layer by 16. Here we have again the original image and the simple configuration with 16 decoders. Then we have the complex configuration where we multiply the number of future maps by 16 with hyperbolic tangent activation function and rectified linear unit activation function. And on the most right corner, we can see the complex configuration with only 2 modes. And here we can already recognize that the complex configuration with 16 modes and as well as the 2 modes are capturing the flow phenomena in a rather good fashion, as the shock is captured as well as the small scale structures are captured in detail as well. And from the first look, we can say that the hyperbolic tangent and rectified linear unit activation functions are doing a pretty similar job in reconstructing the image. But in order to differentiate between those, we plotted a line plot for the u channel, so velocity u at y equals 5. Here on the top line plot, we can see the hyperbolic tangent with the simple configuration, and we can see that the main patterns of going up and down are captured. However, the fluctuations, high frequency events are unfortunately not captured. However, when we look at the bottom 3 line plots, we can see that the hyperbolic tangent as well as rectified linear unit are capturing the fluctuations in a pretty good way. However, hyperbolic tangent is doing a slightly better job compared to the rectified linear unit. And if we focus on the line plots in the bottom 2 images, we can see that the 16 decoder and the 2 decoder methods configurations are doing a similar job, but the 16 decoder is slightly outperforming the 2 decoder configuration. So to wrap it up with the complex configuration, here we have the original image, simple 16 modes, complex 2 modes, and complex 4 modes. And we can conclude that the complex architecture with the less number of modes is already outperforming the simple architecture with the higher number of modes. So increasing the number of modes is a better way to go compared to increasing the complexity is a better way to go than increasing the number of modes in a simple architecture. Then we compared our results with the traditional method, proper orthogonal decomposition, which is known for its ability to handle linear problems. However, it has its limitations when a nonlinearity is introduced to the problem, which we have heavily in our case. And from the images, we can immediately recognize that POD is doing an okay job at reconstructing the flow field, which is also proven by the relatively higher mean squared error. And so POD is capturing somewhat of the large scale structures. However, the small scale structures are nowhere to be seen in the POD's reconstructed image. And here we are comparing the POD with our best model, hyperbolic tangent, with the complex architecture. And it is easy to see that the hyperbolic tangent activation function with the complex configuration is heavily outperforming the POD model, as it is capturing the large scale and the small scale structures in a way better way compared to the proper orthogonal decomposition. So we have the reconstructed images, but what good does it do to recreate the initial image? In order to understand the underlying flow phenomena or make a deeper analysis of the flow, we can take a look at the different decoder outputs. Here we have the decoder output 1 and decoder output 2 for each of our channels for a 2-mode configuration. This is, of course, the complex configuration. And what we can see, which is quite interesting, is that decoder 1 and decoder 2 are capturing different flow features, where the decoder 1 is capturing large-scale structures and decoder 2 is capturing small-scale structures. This is also proven by the line plot for channels U and V for decoder 1 and decoder 2 on the right-hand side, where we see the decoder 1 is following a rather steady trend, meaning there are no fluctuations in decoder 1's output. However, decoder 2 is capturing high-frequency events like turbulent small-scale structures, as it is highly fluctuating. Then we can also deepen our analysis by looking at the mean velocities before and after the shock for y equals 5 for decoder number 1 and decoder number 2, where the mean velocities are decreasing in both decoders before and after the shock, which is an expected behavior when encountering a shock wave. And to conclude this chapter, we can say that decoder 1 is capturing large scale and decoder 2 is capturing small scale structures, and both have trends that are confirming the shock effect. But what happens if we increase the number of modes to 4? Here we can see that decoder 1 output is almost same as the two mode configurations, decoder 1 output and decoder 2, and decoder 4 here are capturing also small scale events, whereas the decoder 3 is capturing somewhat of a large scale event, and that can be confirmed here again by the line plots. Here I excluded decoder 1 output because we already know that from the two mode configuration. And again, when we look at the line plot, we can see that decoder 2 and decoder 4, those are orange and red line plots, that they are capturing high frequency small scale structures with high fluctuating effects, whereas the decoder 1 and decoder 3 are capturing more large scale events, and the shock is here on the bottom visible. When we look at the blue line for the V channel, there is a discontinuity at almost z equals 30. So to wrap it up, I'd like to give a quick summary. So what we had was spanwise transversal traveling waves, where we achieved an average reduction of 26.49% for a Mach number of 0.7. And this was achieved through drifting the quasi-streamwise vortices from the near wall to the outer wall regions, which in turn reduced the Reynolds stress, and hence the drag reduction was achieved. And we could also conclude that our autoencoder had a high ability to handle nonlinearities, where out of the two activation functions that we use, 10H performed in a better fashion. And by looking at the different autoencoder decoder outputs, we could improve our flow knowledge. And in the future, we would do a more in detail investigation of the turbulence statistics, as well as the deeper analysis of the QSV displacements, and their breakups will be investigated, as well as their interactions with the shock wave have to be investigated. Then we will increase the complexity of our autoencoder model, where we will enhance it to a 3D model in order to also take a look at the streamwise flow. Then further hyperparameter tuning is always an option. Decoder outputs definitely have to be investigated more in detail, and then we will compare our autoencoder with dynamic mode decomposition and empiric mode decomposition, as well as running the model again with a different Mach number in order to see how it behaves in a completely unseen data set. Well, thank you very much for your time, and if you have any questions, I'll be happy to answer them.